reservoir flow, please.
Thank you for the invitation for this conference. First of all, I'd like to say that this work didn't work, actually. I just came to show the idea and get some solution for them. I believe that this is not very popular in mathematics, kind of semi-continuous thermodynamic approach, and it might be very useful for problems in which there are many components in some sense. Well, basically, some basic concepts of complex mixtures, a little bit between discrete mixtures and continuous mixtures, some mathematical models, aspects of discrete multi-component approach, and transform this multi-component in a continuous multi-component approach, transform them in moment equations, and then find a solution method by this methodology. And like some applications in Instituto combustion, and some comments, as I don't have conclusions yet. So basically, when you're talking about mixture, you have two or more substances or components. When I'm talking about complex mixtures, I'm talking about an infinite number of components. It means that they are uncountable in some sense, and it's hard to solve it. For instance, when I have our oil, we have, how can I say, an uncountable molecular weight, represent a volume fractions. When I have, for instance, a bubble flow, a particulate flow, a dispersive flow, we have uncountable particle size, a continuous point of view. Like the same way for droplets in particle distributions. Let's see if I can, yes. So the idea is the following. When I model multiphase, multi-component flow, we are talking about discrete molecular weight in some sense. The idea is to transform this discrete mass fraction or molar fraction in continuous functions in molecular weight terms. First, we have mixture density, like the probability, or PDF, the probability of having a molar fraction associated with a molecular weight. A weight mixture that in some sense represents the molar fractions or mass fraction, and the abscissas in these continuous functions that is in some sense for us the molecular weight. Okay? So the idea is to transform this discrete composition in a continuous composition. Why this? Because we could represent infinite, uncountable number of components as only one function. Instead of solving for each component, we are going to solve by a continuous function that have these sum properties. So if I want to represent one average process, I only need to integrate, for instance, the molecular weight of a mixture in terms of this probability function. So I have the average properties, in this case, the molecular weight. So if I want other properties, we can generate other moments in an infinite sense. Okay? Well, if you look for a discrete component equation, we have it in terms of the molar fractions. Okay? And we have, for instance, the Darcy equation as well in a discrete sense. And we have the velocity of each component based also in this molar fraction. So the idea is to transform that equation in an uncountable number, and instead of summing that, I have a function instead of the molar fraction. So the equation is transformed in that sense. And the source term is still a function of these continuous functions. So here we have the mass transfer between phase, and here we have the reaction term in some sense. So the constraint still exists. If I have a semi-continuous function, it means that some components are discrete and other components are continuous. So The constraints for molar fractions can be described like this, where this x represents the discrete component and this function is the continuous component. So if I integrate this equation in terms of the internal variable, in this case the weight, I have the moments also for the source term, right? So the equation that first is in this function, now we are thinking of use the moments of this equation instead of the continuous function. So here are some constraints for the mass transfer term and for the diffusive term and for the reaction term. If you integrate this equation in the whole space, in the whole domain, we reconstruct the saturation equation. It's actually the zero moment of our conservation law for PDF. In some sense, for a compressible case, we can reconstruct, if you integrate the equation in terms of probability function of the PDF, we can regenerate the pressure equation. So that's not dependent of our continuous function. The same way that we know in the traditional conservation laws. Well, the energy equation as well, in terms of our continuum functions, we can see that the temporal term, the convective term, the Laplacian term, and the source term based on the energy transferred by the mass transfer between phase in components and energy transferred by the reaction in some sense. So the equations are equivalent. However, we cannot solve by the continuous function directly. So if we try to solve it directly, we are going to discretize anyway. So instead of discretize the continuous function, we generate an equation for the moment of these continuous functions. It means that we have the statistical representation of the original distribution functions. So for each phase alpha, we have moments k in each phase alpha. So the question is how to solve this equation. Well, we use the approximation of quadrature moment method. So my continuous function is represented by a summation of direct function associated with the weights and by the mass fraction or molar fraction. So this representation closes the moments by a simple summation of these weights, that mass fraction or molar fraction, and its abscisses. Okay? So in some sense, if I introduce this equation, the moment equation, the evolution will be based on the mass fraction of the molar fraction and also by the abscisses. Oh, in other words, the abscisse also moves as a conservation equation. Okay, if I have complex mixtures, while the effects of the reaction or evaporation or condensation happens, the molecular weight of each discrete component is also moves. Okay? So, and also one important property that you can get is if you have the approximation by delta functions, we can calculate integral terms by a quadrature evaluation. So the operations that has quadrature terms can be also computed based on the weights and the abscisses that are the mass fraction and the molecular weight discretized, which moves along the solution. So how we get the weights and abscisses based on the moments? We get that way. There is an algorithm that says, and based on a theorem that says if we have a set of moments in a convex space, we can reconstruct the weight and abscisses from that if it's in the border of the space. our case? So the solution, there is only one solution in this map. We have the solution that are the weight of a direct summation functions. Well, in this case, we're going to use a Euler algorithm that's very well known and stable. Implementation. The next step to implement this new methodology. Basically, we use OpenFlow. That's how can I say, software package that operates tensors. It's a C++ toolbox, actually. Well, the capability of our implementation, we call KeyMon compressible IMPS flow. It's a lot of the algorithm. It's IMPS algorithm for a complex compressible case based on moments. It's generic, three-dimensional case for generic geometries. In other words, unstructured mesh, any geometry can be calculated. Any phase and any C discrete components or two NC moments. Okay? Well, spatial discretization. Finite volume method was used. High order interpolation scheme for gradients, divergent, and Laplacian operators. It means that maybe it's the problem in our case. Temporal discretization, Crank-Nicholson with adaptive time steps. The algorithm is the following. First, we initialize all fields, including the moments of the complex mixtures. When we have IOL, we actually can get these moments. We inverse the moment to get weight and abscissa, in other words, mass fractions or molar fraction, and abscissa, the molecular weights. Solve the saturation equation explicitly. Then solve energy equation implicitly. Then pressure equation, the moment equation, and invert them, and update all properties. So moment equation is solved in explicit fashion. This is the example. We're trying to solve for EOR example that we consider like one single reaction. In this case, the hydrocarbon is our quadrature node that moves along the solution. And from now, alpha phase is considered liquid in gas phase, onto phase for our test case. Well, this is the simple model based on moments. Instead of components equation, we have two moments equation, one for the gas phase and one for the liquid phase. Convective terms and source term, this represent reaction, and this represents vaporization. Okay? Note that we have two NC moment equation for each phase. In this case, we have these submodels that vaporization model. Note that the vaporization is function of the molecular weight. Note also that the Y, actually the fraction, is a continuous function, which is a function of the molecular weight as well in the vaporization term. The reaction term is the same thing. The energy activation is also a function of the molecular weight. Note that everything can be based on the molecular weight. The properties and the equations can change during the simulation of the solution based on the moment transportation of the PDF. In this case, we, how can I say, invented these definitions for these source term parameters. We consider that as the molecular weight increases, the vaporization terms goes to zero. It's physical, written physically. And the energy activation increase with the molecular weight. And these are the parameters, okay, for a test case. We use this submodel for relativity permeability, because with this model can also depend on the molecular weight if you want, but it's not for simplicity. The equilibrium term can be calculated by Claus-Clapeyron equation, and the vaporization term is also a function of the molecular weight. could be any, just to make it more simple. These are the initial conditions. Normally, I can find any other area, whatever. And this is the initial condition for hydrocarbon distribution. We use the gamma function with these parameters, and we use on two moments just as a toy model. With this time step, and so this parameter that this came from Mailybaev, Alexei actually, and we used to simulate the case. Well, it's supposed to be there. Well, whatever. It's a 3D geometry with 5,000 elements, 100 meters of length in x direction. In this we have the delta P variation, right? Supposed to be another thing here. It's not here. And this is the two waves, saturation wave, and this is the oxygen wave. Actually, here it's supposed to be a temperature wave, but not here. My observation is that the wave didn't change with the molecular weights. It's interesting because I was expecting the opposite. As the molecular weight changes, the wave should change too. But it's not in that case. And also the temperature didn't change. I was expecting actually that we have a wave of the molecular weight, as we could try to solve the moments equations as a wave as well, as it's also a conservative equation. Some comments. There are different open challenges here, even for numerical methods, because when the moment goes out the space, the solution diverges. That's very complicated because when I use high resolution interpolation function for finite volume method, it's very common that if the mesh is not so good enough, this can have numerical error that makes the moments unrealizable when it's go out of the space. Since the wave is not going to change due to the molecular weight evolution, and if it's true, this approach is not an option for in situ combustion. Being sincere, I think that's enough in a short. Whatever. Thank you.
So,
very fast.
Questions, comments, please.
Okay.
You put back the previous slide.
This not the.
Why it sinks?
Why what?
Second.
Why? Because I was thinking of apply this for in situ combustion, because I was thinking when we have complex mixture in the oil.
No, that's not exactly the question. Why do you believe that the wave structure is not going to change due to molecular weight diffusion?
Because when I tried to simulate different parameters and it didn't change. I have no mathematical proof, but I tried many times, and the wave is still the same. The difference was the magnitude, of the downstream and upstream values. They change during this, never get the steady state. It's never stable. The waves come like all the time changing, but with the same structure. The structure didn't change. I don't know why. Is there any suggestion or opinion about this?
Please. More questions?
One question.
Please.
Yeah, I'm a little bit confused because I know the work of Alexei and Negar,
I know too.
and you know too, of course. Then the thing is that if I have a light hydrocarbon among heavy hydrocarbons,
I know.
I seem to be able to use hardly any fuel and then produce almost all oil. And if I do not have this light component, then
I was thinking.
Well, it is not a completely different structure. But as an engineer, I would really say, oh, I'm so happy I can if I have a little bit of light component, I can produce almost everything.
Yeah,
So
but
apparently, is that what you are saying? If this is true, this is not an option for in situ combustion. Why are you saying that?
I was expecting, how can I say?
You are
The-
mathematically disappointed or engineering-wise disappointed?
Yes. Yeah, that's the. I'm thinking to apply to another application, but in some sense, if I have very heavy oil, it might be useful if you have a very short range of molecular weight in the distribution and the vaporization is very close. This should be a good application in some sense because we can make the very difference between all components with very short number of, well, how can I say, quadrature nodes. And you can get a better result instead of using a large number of discrete, because the, how can I say, distribution will move while the solution goes to the steady state. I don't know if
But what is exactly not an option for in situ combustion?
what exactly? My how can I say? My approach is not an option in this sense because Alexei get better the same result using a simpler approach. That's the thing that my application could be not an option. If I have the same wave structure, Alexei results better in some sense because it takes a lot of time to simulate with my approach.
Oh, okay.
Let me try a candidate for a conjecture why perhaps it doesn't work. But let me try an electrical engineering language. You use a certain number of moments, right?
Right.
How many?
I use 4, just to simplistic,
Well,
but it could be.
That's projecting in a 4-dimensional space, low frequencies only. So you are throwing away a lot of the high.
Lot of information.
Now a shock is
Sharp.
sharp, and therefore there are plenty of high frequencies.
Mm-hmm.
Perhaps that's the reason.
Yeah, that's what I say. When I use like the numerical method affect the result because of this. If I need to use more moments to kind of write this kind of loss of information, and you also lose it in the numerical methods for a short number of moments. Let's see.
You can ask our numerical analyst for conjecture.
Well, like, why do you use momentum? Why don't you try to...
To discretize, because when I have a complex oil, and we have a process that vaporization reacts, the composition changes along the way. When I use moments, I can kind of conserve the molecular weight, and molecular weight moves during this transformation process. That's why I try to use moments instead of discretize. It's like adaptive way to calculate quadrature points. When you use when a fixed quadrature point, we're using in that sense that engineers are used to fix the points and calculate. In this case, we calculate the moments and move the points of quadrature, that curve, continuous curve.
So we have time for more quick questions, please, Bruining.
Well, I was wondering so very nice mathematical idea, but from application point of view. So usually to determine this activation energy and pre-exponential factors are really challenging, and you need a whole function, continuous function of them. What's your idea? How to obtain?
Yeah, there are some PDF to estimate the reaction. Like we have PDF for this set of components. Instead of use a discrete energy activation, we use a continuous as well, based on data. It's an option, but I'm not sure what you think of using something different. What do you think that can be used? But I believe that if you we can take a lot experimentally or from a bunch of data, a function that can represent the energy activation instead of get experimental data with average value. We can use like a statistical source instead.
Okay.
So, okay, let's thank the speaker again.